Hello all, I am Syed Asrar, a PhD student from IIIT Delhi, presenting the project proposal titled Intelligent and Reconfigurable Deep Learning Augmented Wireless Channel Estimation at Edge. I completed my MTech from Jamia Millia Islamia and then joined IIIT Delhi as a PhD student in January 2021. My research interests are wireless channel estimation, deep learning architectures on hardware, reconfigurable architectures, and TinyML. I have a paper published in IEEE VLSI. Dr. Sumit Darak is an associate professor in IIIT Delhi. He completed his PhD from NTU Singapore in 2013. His research interests are reconfigurable and intelligent wireless transceivers and algorithms to architecture mapping. I will start this presentation by giving a brief introduction of the field and explaining the motivation behind the proposal. Then I will introduce the problem statement and give brief review of the state of the art. Then I will give the detailed description of our proposed system design and the completed work. Finally, I will briefly discuss project plan and then give the closing remarks. Wireless channel introduces fading and adds noise to the transmitted signal. The cumulative effect of fading is represented as channel gain. Estimating the channel gain at receiver by transmitting predefined signals called pilot signals is called channel estimation. Channel estimation is a challenging task, particularly in next generation communication systems due to the introduction of heterogeneous devices occupying same spectrum leading to poor SNR. The challenging channel conditions in next generation communication systems, for example, high mobility in V2X communication, large number of antennas in MIMO, large channel matrix in RIS, adds to the challenge. Our work will focus on vehicular communication where the channel is doubly selective channel with very high Doppler. V2X communication enables vehicles to wirelessly exchange information for road safety and traffic management. It is governed by IEEE 802.11p standard, which uses block pilot pattern where the channel is estimated at the beginning of the frame using a preamble and then updated using decision feedback. More recently, a new standard IEEE 802.11bd is introduced, which has a midable to allow channel estimation within the data frame. The conventional estimation techniques use demapped subcarriers as virtual pilots to update channel estimates within data frame. This introduces demapping errors, especially at low SNRs and high modulation schemes. These errors can propagate due to feedback. More recently, deep learning based techniques are introduced for effective channel estimation. But introducing deep learning in wireless Wi is a challenging task due to the low latency requirement of wireless communication. Also, as most of the receivers are on battery powered edge devices, the area and power requirement should also be low. DL performance is training dependent, and deep learning model trained on one channel condition do not generalize well for different testing conditions. Limited hardware availability for on-device training adds to the challenge. The above factors motivates the need for low complexity reconfigurable deep learning based channel estimators that accelerates the estimation process and makes it flexible for different channel conditions. Our goal is to develop intelligent and reconfigurable architectures for deep learning based channel estimation in vehicular communication for edge platforms. The main objectives of our work are to propose low complexity deep learning augmented channel estimation for IEEE 802.11p and BD based V2X communication, explore hardware friendly fixed point deep learning based architecture via quantized training approach, develop and benchmark software and hardware IPs for conventional and deep learning based channel estimation, propose algorithms to incorporate intelligence in the dynamic RF environment, develop RF SoC based end to end system level demonstration for real radio environment. DL based Phi is attracting a lot of attention recently in both academia and industry, with 3GPP expected to include some aspects of AI/ML in the upcoming release 18. DL based solutions can broadly be classified as end to end solutions and block based solutions. End-to-end solutions replace entire transceiver with a deep learning model. While it provides global optimization, but it requires a complete rethinking of communication system design and is not compatible with the standards. Block-based solutions aims to replace one or more signal processing blocks with deep learning model. Replacing single or a multiple models may provide better performance, but it requires a complex deep learning model. Augmenting a single signal processing block with a low complex TDL model is shown to provide better performance at low complexity cost, as it incorporates expert knowledge and is thus preferred choice for hardware implementation. Our design falls in the category of deep learning augmented channel estimation, where conventional estimation schemes in IEEE 802.11p are augmented with low complexity deep learning model. IEEE 802.11p follows a block-based pilot arrangement where long training symbols present in the preamble are used for channel estimation. After initial channel estimation, data pilot aided schemes are used to update the estimation for data symbols. Once the channel is estimated using LTS, the estimated channel is used to equalize the first data symbol. The equalized data symbol is demapped to nearest constellation point, which is treated as a virtual pilot to compute the final LS estimate. This gives the DPA channel estimate. DPA scheme assume that channel does not change significantly between the adjacent symbols. The DPA estimates are further refined in STA scheme by taking the frequency and time averaging to reduce the effect of noise. TRFI scheme employs a reliability test to check the reliability of virtual pilots. If the current DPA estimates demaps the previous data symbol to same constellation point as the previous estimate did, then the current DPA estimation is reliable. Interpolation is used to get the estimates for unreliable subcarriers. TRFI performs better at high SNR conditions. Output of conventional estimation schemes is further refined by a low complexity, fully connected deep neural network model, which reduces the effect of demapping errors. Simulation results show the performance improvement over the conventional schemes. DNN augmented schemes follow the pattern of conventional schemes. STA-DNN performs well in low SNR region, while TRFI-DNN performs better in high SNR region. Thus, for optimum performance in entire SNR range, the algorithm should switch between these two schemes based on the received SNR. Also, the DNN performs poorly if training and testing conditions are different. One solution the, is to have all the different algorithms and deep learning models on the FPGA and select the appropriate one as per channel condition. This is not feasible from memory and power consumption point of view. More feasible solution is to use FPGA's dynamic partial reconfiguration property, which allows time multiplexing of hardware modules so that only one of the modules is present on FPGA fabric at a time, and the module can be reconfigured on the fly automatically under software control. For ASIC platforms, multiple DNN modules can be stored in the memory, and the desired model will be loaded. As DNN architecture is same, memory-based reconfiguration provides the required flexibility at ASIC level. Now, this requires some sort of intelligence in the system to sense the channel conditions and make decision as to which estimation scheme is to be used. This intelligence is provided by another low complex TDL model, which takes in the LS estimated channel and outputs the underlying channel model. Dimensionality reduction technique PCA is used to further reduce the complexity of the model. We have simulated the classifier under zero Doppler conditions and got about 99% classification accuracy. The classifier powered channel estimation has almost the same NMSC and BER as selecting the actual channel. On-device training is also being explored as a solution to varying channel conditions. A recent paper has presented a simulation model of on-device training and proposed that using a pre-trained model as initialization to on-device training reduces the training time. For this purpose also, the channel classifier can be used to select the appropriate model for the initializer. The desired channel estimation algorithm and intelligence will be incorporated in an end-to-end hardware prototype on Zinc RFSoC platform, consisting of quad-core ARM Cortex processor, ultra-scale FPGA, and RF front-end with high-speed ADCs and DACs. Hardware-software co-design approach will be used to implement the transceiver functionality in the processor, while the channel estimation and classifier will be accelerated on FPGA. The received signal after FFT is passed to the channel estimation block on FPGA, where initial channel estimation is performed, which is then used to classify the channel model. The output of channel model is sent back to the intelligence unit on PS to select the appropriate DNN and using dynamic partial reconfigurability of FPGAs, reconfigure the DNN module. Estimation module is reconfigured using the SNR information obtained from the preamble in PS. While DNN is being reconfigured, the estimation module computes the channel estimates. The output of DNN is sent back to PS for further processing. In our paper published in IEEE TVLSI, we have implemented DNN augmented channel estimation for zero Doppler conditions on SoC. The performance is better than LS and LMMSE, while latency and resource utilization is very low compared to MMSE. We also designed a GUI based application to see the estimation performance in real time. For IEEE 802.11p based systems, we have completed the design and implementation of conventional STA and TRFI estimation schemes on SoC. We achieved 2 times acceleration for STA as compared to the PS implementation and 3 times acceleration for TRFI estimation. The next task in algorithm design is to design a low complexity deep learning augmented channel estimation for IEEE 802.11bd standards and exploring the quantization aware training and on device training for deep learning algorithms. In hardware design, next task is to design and implement software and hardware IPs via hardware software co-design and word length analysis. Finally, the system design for end-to-end PHY incorporating intelligent and reconfigurable channel estimation will be developed and its performance will be evaluated in real radio environments. To sum up the presentation, latency and hardware resource utilization are the main considerations in implementing deep learning in wireless physical layer. Implementing the design on a system on chip platform is crucial for thorough analysis of performance, latency, and area utilization. There is no one solution for all channel conditions, and hence reconfigurability at hardware level is must to get the best performance under all channel conditions. Intelligence is required to sense the channel condition and select the best optimal solution. We have been working on this project from last couple of years and have published one paper in IEEE TVLSI. We have also worked on DL-based channel estimation for COMB pilot-based OFDM systems used in cellular communication. We presented a demonstration of the above work in a design contest conducted by VLSID 2023 and emerged as runners-up. Thank you all.